guys, we're going to get going. So I see the rain coming in. You know, if you come on time according to our schedule, you don't get wet. So, anyway, I'm delighted to present Matt O'Donnell from the University of Washington in Seattle, which is weather not too dissimilar from this.
For 6 months of the year.
For 6 months of the year, and Matt has I shouldn't say long, it's a great background in this, but what maybe is unusual about Matt is, from the other speakers, is that he has spent some significant time in industry with GE,
right.
And has all that experience to bear on things. He spent time as Dean of Engineering
I'll talk about
in Washington.
So sit down.
And so on.
Okay. Wait till we're on. That's it? Okay. So let's get started. So I'll introduce myself and a little bit about the place in the next slide. But what I thought I'd do, because I know there's stragglers. There are always stragglers. So know that you are here first. You know exactly what we're going to do. We can follow. Those who come in late will be totally lost. Okay? And then we'll have a quiz at the end. So, 3 principles. To understand photoacoustics, you must first learn something about acoustics, right? Or ultrasonics. It's a little tautological, but that's all right. To understand photoacoustics, you must first learn something about optics and photonics. Makes sense, right? See, they're going to be really lost if people come in late. So what are we going to do? Well, I am your comic relief. Okay? I'm not an optics guy. We do a lot of optics, but I'm not an optics guy. All right? I'm an ultrasonics and acoustics guy in MRI. So I'm assuming, though, based on what I've seen this whole week, you all are primarily optical people, some biological people. That part we have in common, so we can talk about that as we go through. But most of you have no clue what ultrasound is. Some of you have seen it in some courses, probably. But I have a feeling very few of you have actually practiced any ultrasound. How many have actually played around with the ultrasound scanner? A couple? Okay, yeah, that's what I was expecting. So we're going to focus this first part on ultrasound just so everybody has a base. And when you leave here, on your certificate it will say ultrasound expert as well, right? So you can check the box and you can show it to your faculty where you go back to. So about me. So it's another thing I always do. I always tell students in classes I teach is you should be able to tell your life story in one slide. And you should do it routinely and get used to talking about yourself. I know this is very American. I apologize. But it's very American because we go out and like to start companies and do things like that. And if you cannot do this, nobody will give you a nickel. All right? So, New Yorker, training, postdoc. One unusual thing is I spent 2 years in the medical school as part of my training. Then, as Martin was trying to say before I rudely interrupted him, is that I spent 10 years at General Electric, research and development, MRI and ultrasound. I was in the original MRI group, brought out the high field scanner, and I started the ultrasound group, which eventually led to the Logic projects. I then went to the University of Michigan, where I was there for 16 years. Part of that move is that I was one of the 4 people that started the Biomedical Engineering department, and I was chair of that department for a while. Then 10 years ago, I went to the University of Washington. So I notice in Asia, when we say the University of Washington, everybody assumes we're in Washington, D.C. Right? And then the second part, we say, no, we're not Washington, D.C. Oh, St. Louis. And then we say, no. But as soon as we say Seattle, everybody understands where we are. So we are in Seattle. I wish we were called the University of Seattle. It'd make life much easier, but it's not. It's the University of Washington. I'll talk about that in a minute. Okay, and I went out there to be dean for a number of years. I stepped down about 2.5 years ago, which was a lot of fun because it was 65 now. It was 60, just turning 63, so it was about 2 years ago. It was okay. You start as a scientist and engineer, last phase, last 5 or 10 years. Do you want to do it being an administrator or doing a little science and engineering again? So it was a conscious decision to do that, so I've been back about 2.5 years. But my focus over all this time has been on biomedical imaging and medical devices. And like I say, MRI and ultrasound, and I put it in optics there, but not optics like you all do. Optics, as you'll see, more integrated into ultrasound devices. And molecular imaging and therapy has been the focus probably over the last decade, and in the last lecture I will talk about that. But the best job in the world I have is the one shown at the bottom, which is I have 2 grandkids, and one of them, the little guy right there, lives in Seattle, so I take him for a little while every week, which is nice. It's hard to do when you're a dean to do that. When you're a professor, it's very easy to do that, so I like doing that. Okay, so what we're going to do. What we're going to do is, like I said, first is an intro to ultrasound, and we'll go through that. Then, in the second part, I'll do the why and what. So, what is photoacoustics, and why do I care? And I'll kind of do them backwards. I should tell you what and then why, but I'll tell you why first, then the what. Then we'll take a break, and then after the break, we'll do how. Okay, so the first part of after the break, the how, will be how do you make a photoacoustic image. Okay, there's lots of different ways. So I'm going to go through that. And then the last how is how do you do a molecular image with photoacoustics and ultrasound. Okay, so why ultrasound? Well, I always like to show this slide first because it's, if I can do something with ultrasound, I will always win. That's sort of our philosophy, my philosophy for over 30 years. If you can do something with ultrasound, you will win. Why? It's low cost, no radiation, totally non-invasive, highly portable. Look at these 3 systems here, and these are older systems. If anybody thinks, this will be recorded, so I'll say it. Lumify system from Philips is the latest one of these systems. It is unbelievable, the image quality in that, and you plug it into a Samsung Galaxy. Okay? Real-time, fundamentally real-time imaging, which means you not can only do diagnostics, you can guide procedures, which is done all over. What's the impact? 50 million echocardiography exams are done every year. Just echocardiography in Western Europe and the United States. Several 100 million ultrasound exams are done between Western Europe and the United States total every year. Worldwide, this is an estimate. We have good numbers on Western Europe and the United States because of business purposes and marketing. But an estimate is that there are 1 billion ultrasound scans per year worldwide. Okay? By far the dominant imaging modality for diagnostics. And I would argue it's probably the dominant diagnostic tool in medicine if you integrate it across worldwide. So it has that kind of leverage and impact to allow you to do things clinically if you can get in there. All right? But you can't do everything in there. What can you do? Okay, so this is a circa about 15-year-old machine. And I just showed this to say, have you seen one of these? Right? You've seen that? You know what it is? Ah, very good, very good. Bunch of bioengineers there. Okay? So first thing you see is that I see a heart and the heart's beating. Right? That means the image is real time. Now this is an old scanner. This is scanning at about 30 hertz or so. But the typical frame rates on ultrasound scanners, depending on application and trade-off with image quality, is from about 30 hertz up to several kilohertz. So you can do several kiloframes per second. With ultrasound, you sacrifice a lot of image quality to go at those high rates, but you can do it. Okay? So you can see valve leaflets, etc. That's in there. But you also see other things. You see speckle. Right? We've seen speckle a lot this week. But you can see speckle in there, and that's because it's a coherent imaging system. So when you look through, you can see these kinds of things that you can read out from a typical echocardiogram. Okay, it's real time. You can tell the difference between blood and the walls. Why? Because their scattering coefficients are fundamentally different in ultrasound. You could see all 4 chambers of the heart working in parallel. And so what do you do with something like this? Well, like valve function. Very, very easy to assess valve function with these types of images. Okay, so what's this one? It's a heart. Okay. Now the image quality is a little less. I guess this is about a 15-year-old machine. It's a little bit less, but you can see the chambers and all that, right? So that's the heart inside the fetus, inside the womb. Okay. Now this is third trimester stuff, but you can see, you can evaluate valve leaflets. You can do all the same types of things in there. Okay. So in that, what do you notice? Well, first of all, it's a fetal heart, like I said. You need a higher frame rate to capture, right? Because the heart's beating faster. But you have that opportunity because it's closer. So your propagation times are smaller, so you can go faster. Need higher resolution to capture. Okay? And that turns out to be shorter wavelengths or higher frequencies. All right. So let's go from about the 15 years ago in the traditional, because this world has changed a lot in the last 15 years. It's changed in two ways. At the high end, it's changed in terms of the image quality and the types of measurements you can make. And at the low end, it's changed into these little handheld devices, which are pretty much ubiquitous now in the developed world and spreading rapidly through the developing world. So you're used to a traditional 2D ultrasound picture, as shown here, the cross-section through a fetus again. However, there are now real-time 3D scanners. We use the buzz phrase 4D, so I saw that up here on some slides earlier. The 4D has been a standard ultrasound phrase for a while, but now it's become a clinical reality. What's interesting is nobody looks at the 4D image. Can you look at a 4D image? If you can, please, please. The bar tonight will have another session of trying to figure out how things work if you can show me how to look at the 4D image. Right? All you can see is 2D plus time. Right? However, what they do, how this is displayed, is in real time, it displays multiple cross-sectional views in parallel. So you can look at the multiple views in parallel, and usually that's done to orient the transducer, so then you will acquire a short segment of the 3D. Again, it's all real time, so there's no take it offline, reconstruct, etc. The data is all fundamentally real time, but then you can put it together again. This is just too much light in these things. Guys in the front maybe can see this. You see the fetus there? And the fetal face? Yeah. I think it's mother's son in Ireland.
Down the other thing.
Yeah, we'll just wait a while, right? Okay, so you can do this profile. Can you read that or see that? Did your parents ever tell you about putting your foot in your mouth? Okay, so it's there. You can see the full face has 27 weeks. And then this, at least in the United States, is usually what most parents, so the standard in the United States is 2 scans. Normal pregnancy, you have one early, just to make sure that the fetus is, attached to the uterine wall, it starts developing the uterine wall, and is right size and volume at particular dates. Then the last, and then normal pregnancy at the end, what you're looking at is to see if there's any delivery issues. And so this is usually one of the late stage ones, and most parents come home on their iPads with one of these loops. And what you get when you go home is something like this, and you can look at the kid, and that's the way we found about our grandkids. Is my son came home with his iPad, put it down while we were fixing dinner, played the button, showed one of these. And my wife went, "Oh, that's cool." And then I looked at it and go, "Oh, I know what that is." So clearly can tell. That's not an O'Donnell. So amazing things that you can do with very, very simple technology. So now the last point I want to make is that you can also see a lot more in anatomy. And this is the simplest of these types of measurements, which are fundamentally functional measurements. And so this one is what? What is imaging? It's the heart. Okay? But I see colors in there. What do the colors have to do with? Blood flow, right? Right? And red and blue, toward and away. Now, do you think somebody goes in there and quantitatively looks around for the flow patterns and all that? No. What do you think's going on in there? Any clue?
Some Doppler.
Well, it's Doppler, but what medically is going on? Yes, exactly right. Very good. So we do have some biological people and medical people. Regurgitation. Okay, so I'll show you. This is the mitral valve. Okay, and Irina yesterday was talking about development of the heart, and so they had these flow pumps where you had forward and retrograde flow. That's before you have the valves. Once you have the valves, you should not have any retrograde flow, right? That's why you have the valves. So here what happens is that mitral valve is leaking. How do I know it's leaking? Because I should see one phase of flow one direction and the other, and you see this jet of flow coming backwards into the atrium, which means there's a hole, or not overlap in the mitral valve. So you put that on there, 10 seconds, diagnostic of regurgitating mitral valve. Somebody would be taken into cardiac catheterization immediately, something like that. Okay? So that's the way it is. So functional measurements. Many different types of function. You can look at flow. You can look at elasticity, so how hard or soft things are. You can look at lipids versus waters. You can use multiple types of contrast agents, which are mostly blood analogs. So you can look at perfusion. You can look at a lot of different things which are related to basic physiological function with ultrasound. Again, all leveraging off of this real-time imaging capability. Okay, that was the blood flow. Okay. Next point. I'll tell you what ultrasound is in a few minutes. I always like to try to motivate a little bit why you should be interested to find out what it is. Okay, the other piece, which is not really well appreciated, although Martin appreciates it, just has this constant wrong, but is to appreciate is that it's fundamentally multiscale. What I mean by that is the Martin's formula, the penetration and the resolution are linearly related, meaning that there's a constant between them. So if I want to go deep, I have to use longer wavelengths, so I have less resolution. If I want to go shallow, I can go to higher frequencies, shorter wavelengths, and get high spatial resolution. So these are three images. So the one at the top right is just taken from the scans I did before. Those are typical adult cardiology or adult radiology scans. They typically run at about 3 to 5 megahertz, and I'll calibrate what that means on the next slide. The lower center one is an intravascular ultrasound image. So this is done in interventional cardiology. And you're imaging from the inside out. So the imaging array transducer is in the catheter itself, and you're looking out around it. And so you're looking at the coronary vessel like this. This is not a coronary vessel, which you would like to have. Do you know why?
It's a blood valve.
Yeah, it's totally occluding plaque, just about. That one region right there is the only place where blood flow is going through. Okay. That's done at about 25 to 40 megahertz because you do not have to penetrate very far. You don't care very much, although you care a little bit. You usually like to see one after you've done procedures about restored blood flow. But generally, you don't need to look more than about a centimeter and a half away from the imaging array. The top, you know what that is? Guys are good. All right, that's an eye. Okay, so you're coming in from the corneal scleral junction. All right, it's not OCT, although it looks just like an OCT picture. Right? It's not OCT, but that's done at 100 megahertz, which is a 15 micron wave. So that's why it kind of looks like OCT, because you're about 15, 20 micron resolution. So not as good as OCT, but still in that same kind of level. But the penetration there that you can have is 5 to 10 millimeters on that order, easily, okay? So, you can do this trade-off, and this trade-off is done all the time. That's why, if you ever go to an ultrasound scanner, you won't find one probe, right? The little wands that you use, you'll see 3 or 4 hanging off the side. It's because what you're changing is you're changing the frequency, and you're changing the aperture size that you're using for making the images, because you're trying to always optimize for what your job is. You've heard that all week here, right? And within an ultrasound machine, what you're optimizing is between the size of the aperture and the imaging frequency / wavelength. Okay, so when you look at this, is you can now calibrate this law, and the number I came, after Martin said is 200 the other day, I went back and calculated, it's more like 500 for ultrasound. Because your axial resolution is at worst a wavelength, can be a little bit less, or can be quite a bit less than the wavelength, but typically if you want to pick a number, it's the wavelength. So if you're 5 megahertz, you have 300 micron axial resolution. Characteristic dimension means sort of what's the diameter of a voxel size, and that's about 500 micron. And I always put the voxel. I put this up there just for you to remember, because when we come at the very end, just before lunch, I'm talking about molecular imaging, is I want you to walk out of here with a view or a feeling that you can think of molecular imaging as being able to do a molecular assay. Okay? Just like you take a piece of tissue out and do a molecular assay inside the body at the position you want using the imaging system, but the volume of tissue that you are analyzing is what that last column says. That would be the voxel size. So it's equivalent to, so the image volume that's contributing to a signal that you would measure at 5 megahertz is quite large, under 50 nanoliters. Okay? But as you go down, or if you go up in frequency, down in wavelength, you start to see that you are sampling quite small volumes. So what you do in peripheral or carotid arteries, skin, what do you do with the skin? What was your frequency? Do you know? You see the skin scanner?
20 megahertz.
Yeah, so in this range, 15, 20 is peripheral. We call it within the ultrasound industry, it's usually called small parts. I always like that. But it's 15 megahertz. Wavelength is at 15 is 100 micron. Characteristic dimension, you're down around 5 nanoliters then. The endoscope and IVA system to show you is 25 to 40, and 60 micron resolution, you get about a nanoliter. When you get up to around 50 megahertz, and especially when you get up more, on the order of about 100 megahertz, you get well sub-nanoliter sample volumes, and resolutions in the tens of microns. Okay, so 20, 30 microns. Again, you trade this off for the particular application, and that trade-off is fundamentally the probe that you build, the transducer that you build. Okay. So why do I love ultrasound? Every time I try to get away from ultrasound, it always pulls me back in. And it pulls me back with a lot of other things associated with it. But it pulls me back in is because it's an amazing technology which is very cheap, rides electronics curves, all that stuff, but is a vector to compositional, functional, and I hope by the end of this, I'll convince you also to molecular information in a clinical setting, not in a research setting, where we obviously work in the research setting all the time, but it's a method to rapidly get things into a clinical setting because you're leveraging this 1 billion per year scan industry that's already out there. It rides the electronics curve, so anytime there's changes in electronics, just like with the cell phone, it was within a year or two of the first cell phones coming out, people had cell phone scanners. Okay? Now, they were crummy, but they had them because we're just used to riding electronics curve. Now they're really good, but you do that. Okay? And it allows you to translate. The most overused word in biomedical research of the last 10 to 15 years is translate. Nobody can write a proposal nowadays unless they have it there. We're going to translate this towards a clinical application. All right? But to actually get something in the clinic is exceedingly hard for routine use. This is a means that allows you to get stuff into routine clinical use in a straightforward path. Okay, so what is it? What is ultrasound? Okay, well, it's sound, right? And it's sound that propagates through a medium, such as a gas, a liquid, a solid. Okay? When we say ultrasound, why we use that phrase is we're talking to sounds above human hearing. So that's generally accepted as 20 kilohertz. You know, for me it's like 3 or 4 kilohertz, I think. But generally accepted as the 20 kilohertz. So anything above 20 is considered ultrasound. And that's right. So but it goes Oh, well, I'll give you the sound scale in the next one. Okay. So where is ultrasound to sound scale? Okay. So you ever heard that one before? Infrasound. That's the long, very, very long wave. That's actually used in military and remote sensing kinds of things. Okay? Acoustics is what you know, what we're doing right now, how I'm communicating. And that's typically from this 20 hertz transition up to, or for you all, 20 kilohertz. From ultrasound, typically we're talking about from 20 kilohertz up to hundreds of megahertz, and then above hundreds of megahertz. Usually gigahertz is the real traditional definition. We talk about hypersound. Okay? So for medical, what we're typically talking about is about half a megahertz for some therapeutic applications, go down to half a megahertz, and imaging will go up to several hundred megahertz. About 200 megahertz is the highest for practical applications, although there's certainly been imaging systems built up in the 500 to gigahertz range for research purposes. And you can buy commercial, I think Olympus still has one, a commercial ultrasound microscope which functions in the gigahertz range. That's usually used for materials testing. So in the biomedical regime, we're typically talking roughly from a half a megahertz up to 200 megahertz. So that's a very wide range, right? So I love looking at these graphs where you have your wavelength range and all the optics, right? And the world went from about 200 to about 1.2, right? About 200 nanometers to 1200 nanometers, okay? Look how many orders of magnitude in wavelength we deal with routinely. How do we do that? The probe. Simply by changing the probe. Okay, so first quiz question. This is a solid or a liquid, and I have, or semi-liquid, and I have just made a grid so I can look at little volume elements, little material elements in there, and I now start a mechanical disturbance that propagates. So it's a propagating wave that goes through the material. Okay? Is that a sound wave?
No,
Why not?
because that's short wave.
Very good. So we got some physicists here too. So a standard, at least where places I've been and questions I've asked, a standard PhD qualifying exam question is how can you tell the difference between the gases, a liquid, and a solid? And if you know this, you say a gas and a liquid, at least a pure liquid, Newtonian liquid, cannot support a shear wave. Right? So, that is not an acoustic way. That is not the way I am communicating to you. No. A+. Okay. Ultrasound is a compressional wave. It's a wave in which the volume of the material changes. So how many people have heard, especially the biomedical people, that water is incompressible? Right? You're doing a little mechanical setup and you say, okay, I have this tissue and it's going to deform this way. And here's the water is incompressible. Right? Water is not incompressible. If water were incompressible, the sound speed in water would be infinite. Okay? Every material is compressible. It's a matter of degree. Okay? And it has to do with ratios of moduli. So we usually say water is incompressible or soft tissue is incompressible because the volume changes, the moduli describing that versus the moduli describing deformations of a soft tissue is 4 or 5 orders of magnitude different. So you can separate them and think about them. But fundamentally, it is compressible. And it's that compressibility which is used to propagate a wave. So this is a sound wave. Okay? It's a longitudinal wave. So the displacement of the wave is along the k vector. Right? So the propagation direction, the k vector, and the volume change are all along the same direction. So if you look at that unit example in there, you are stretching and shrinking that volume. So that's called compression when it's taken in, and then rarefaction when it's taken out. All right? So you're moving towards a compressed medium, back towards a negative pressure, right? You rarefy, trying to create a vacuum. Ooh, remember that. We're going to use that effect later for some molecular imaging stuff. The fact that the negative lobes of an ultrasound wave are actually a rarefaction. Okay, so there's physical parameters which you will go through that describe all that, just like you go through with dielectric constant and other parameters that you have in terms of describing electromagnetic propagation. You have a set of parameters here, which are from classical physics of displacements and particle velocities, force or stress or pressure, the mass density, the stiffness or spring constants. When done in a continuous medium, we talk about moduli, and that's the bulk modulus. And then for losses, it's usually viscosity, which is the primary mechanism for losses, although there's other mechanisms for losses as well as viscosity. I'm not going to go through any derivation. I'll do a little bit of derivation for photoacoustics, but here I'll just sort of state things, because all this is an application of two laws. Newton's second law in a continuous material, okay, and Hooke's law in a continuous material. So F equals minus Kx, right? F equals Ma. But as described in a continuous material in terms of its effective stiffness per unit volume, which is moduli, and mass per unit volume, which is density. When I do that, I get a wave equation up here, which when I solve for the wave speed, I find out that the wave speed is the square root, so square root of k over m. The analogy here is the wave speed for the sound velocity is the bulk modulus, which is in gigapascal, typically, okay? And the density, which is the mass density, not charge density or anything. This is very classical mechanics here. And how, to give you a feeling for that, what is that number? It's 1,500 meters per second, 1.5 millimeters per mile per second. Now you're optics folks, right? So that seems slow or fast? Really slow, right? Really, really slow. All right, now we're going to take advantage of that when we get into photoacoustics. We're going to take tremendous advantage of that. All right? When we get into photoacoustics. But since I've been doing, in some way or another, been involved with ultrasound for over 30 years, is that in that time it's been very interesting. When I started, the speed of sound was very fast. Felt very fast. And this is relative to making imaging systems and the electronics that you need to do real-time imaging. So when I started, the speed of sound felt fast. Then in sort of the early 90s, that kind of period, say 25 years ago, the speed of sound was just right. Okay? Now, 25 years later, the speed of sound is too bloody slow. All right? Why? Because you're electronics. Right? So in the old days, people were working with 5 and 10 megahertz clocks. Now you work with multi-gigahertz clocks. And you'll see as we start to make pictures how that comes into play. But anyway, even though the clock speed on your system changes, the speed of sound doesn't change. So you're working with this. So 1.5 millimeters, so this is the way we think about it, because you're looking at it in images in terms of millimeters, 1.5 millimeters per microsecond.
Is this speed in tissues or?
Yeah, that's in tissue. Water, tissue, they're all roughly the same. It does vary. It varies by about 100 meters per second from that value going over the wide range of soft material. Oh, hard materials are different. So bones, quite different. Bones probably over 2,000. Yeah, it is over 2,000 meters per second. But it's a very small range in velocities in soft tissue. Okay. Huge range in shear modulus in soft tissue. But in bulk modulus, which determines this, a very, very small change. Okay. Again, not to bore you with the derivation of the equations, but just to note, in the same way that you can think of a characteristic impedance for electromagnetic wave, you have the same principle with an acoustic wave, and so you have the characteristic acoustic impedance that's in there, which is again related to these fundamental constants, and the simplest way you can think of it is the mass density times the speed. Okay? So you have a wave equation. Okay, now it's different, it's this longitudinal wave, but you have a wave equation, you have a wave speed, you have an impedance, so you're good to go, right? Because if I put up all these different kinds of diagrams, or wave diagram, refraction, reflection, scattering, all these types of things, you know what to do. Right? All you guys know exactly what to do. Now, there's little differences. Where the differences come in, what you have to worry about is when you start dealing with real solids. And the reason for that is that in a solid you can support both shear and longitudinal modes whose wave speeds are close. And because of that, you can have different kinds of mode conversions. So that's really that area, and that comes into play when you're building transducers and other things like that. And we're not going to talk about that at all. But other than that area, this is very, very straightforward because it's a single mode. And so you can think of it as about the simplest of wave propagation in terms of scattering, reflections, refraction, and just use it by analogy. Okay? So that part's cool. How do waves propagate in the body ultrasonically? Okay? Well, it's the exact opposite of light. In light, as we saw multiple times with these beautiful diffusion simulations, is you don't go very far into tissue before your light has been diffused, right, from multiple scattering. The good news in ultrasound is that the scattering is very weak, so from a propagation standpoint, it can propagate in very, very far. Right? And the fundamental loss mechanism, again, you had great lectures yesterday, we have scattering and absorption components, just like in optics, is it's all absorption is your loss mechanism. The scattering is fundamentally very, very weak, and that's because the impedance or the effective scattering coefficients and all that are very, very small. Very small at any given wavelength, a very small, getting a good storm. So I can say anything, right? It can't go anywhere. So most of it gets through other than the absorption. And because the absorption scales linearly with frequency, that's where you get this beautiful trade-off between depth and resolution. Right? As you go up in frequency, attenuation goes up proportionally. Because the scattering really doesn't matter. There are exceptions, but not many. Okay, so you can get through pretty easily, but you don't get much back. Okay? So the good news is it gets through very easily. The bad news is what's coming back to you is very weak. Now, fortunately, over the years, and this is where a lot of the research and certainly a lot of the development that's done in companies is those little probes, those little things that people carry around and drop on the floor and pick up and just stick on jello and then stick on their neck and all that stuff. There's actually very, very, very sophisticated physics involved in there to be able to try to detect acoustic level a few dB above the thermal acoustic Johnson noise in the medium that you're looking at. Okay? So I'm just going to say you can do that. I'm not going to go into that. That's part of an ultrasonics course. Oh, by the way, in the slides, at the end, so when you look at it online, on the back, which I won't show here, is all hidden. I have about 15 slides, which is just the topics you would get in a typical ultrasound course. So if you, and a book, a reference to a book if you want to go look at it, to just look at some of these advanced, like transducers, because I'm just saying that works. It's very, very sophisticated designs to go into those, but it's trying to make sure that you're really detecting at Johnson noise levels, acoustic Johnson noise levels, because the reflections that you get are very weak. Okay, so it's nearly unity, you can totally see through boundaries. All right, so every once in a while this is the standard thing I do, because I know my attention span is short. So I assume the rest of the world is just like me. So every once in a while we'll have a little recap. What do you need to know, right? So you heard a bunch of stuff. So this is what you should take away and then think about. And then if you want to go back and look at some of the slides, especially the references and things which are at the end, which I don't show here but will be in the slide deck. All right. Sound is an oscillating pressure wave, a compressional wave, a longitudinal wave, a P wave. You'll hear those phrases all the same. Okay? The sound speed is determined by the mass density and the bulk modulus of compressibility, which is not very, very much within different soft tissue types. Does vary a lot when you go into either hard tissue or into solids, such as you have in the transducers. Loss of wave physics apply. Okay, it's what I found interesting because I came up through physics, and I remember doing scattering equations in quantum mechanics that when I went to acoustics, I was doing scattering equations and they looked the same. They looked exactly the same. Then when we got into the optics stuff, started looking at this because some device things we were doing, looking at the scattering equations, they're the same, right? And it's dielectric constants versus atomic parameters versus acoustic parameters, it's all the same. But it's waves, right? It's waves. And so you know all that stuff. So you can very quickly get in, and it's just a matter of getting the intuition of what those physical parameters mean. The heterogeneity in tissue are very small, and there's a good news and bad news. The good news is you can get through it pretty easily. The bad news is the signals are very weak. So you have to have very, very well coupled, efficient transduction to be able to see that. Okay, basic imaging principles. How do I make a picture? What was just like OCT? Did we? He isn't jumping up and down. Okay. Remember what he said? What Adrian said?
Nothing like OCT.
There's nothing like OCT. Okay, so ultrasound is nothing like OCT. Actually, it's much easier than OCT. Why? Because you got two things on your side. Okay?
It's okay. Just wanted to answer the question.
Oh.
You can do it on your own too if you want.
Right.
You can just directly record the wave that is coming back.
Right.
The speed is slow.
Right. So you directly record, right? So I get amplitude and phase, I get the full time domain waveform. When Tom was showing the time domain, that's the intensity waveform. No, we get the actual fields, right? So you get that, that's there. So you get to record the waveform, right? That's number one. And number two, the second, which is a consequence of the wave speed being slow, is, anybody know the Rolling Stones? These guys know who the Rolling Stones are. You guys know who the Rolling Stones are? Okay, so when you go home, or when when you're flaking out and you start to put your headphones in, don't worry, I won't notice, but when you start putting your headphones in, the time is on my side. Everybody know that Rolling Stones song? These guys know that. Right? Time is on my side. Ultrasound. Time is on your side. Okay? Because I can make a new lens every single pixel in an image. Alright? So when I saw the optics guys worried about doing these things and playing and getting different lenses and all, it's like, who cares? I just reprogram it. And what I'll show you, what the difference is happened over time. So that sound used to be fast, sound used to be all right. Now sound is slow. Is that now literally every pixel in a traditional ultrasound image is a perfect focus in one direction and a semi-focus in the other direction. And it's moving very rapidly. The latest generation in research, which will be out in clinical scanners probably within the next 5 years, is that every point will be confocal. So every point in the 3 dimensions in an ultrasound image will be confocal in a little while, because you have time on your side. For those of you who have no idea what I'm talking about, is Rolling Stones, time is on my side. Put it in your head, okay? And think ultrasound. Okay, so how do we do it? The way we do it is pitch and catch. Okay? So I launch a wave. And think about clocks, because we're going to come back to clocks. So I launch an ultrasound wave. Would be my clock? Okay, so you have to be very regular. Can you do that?
Yeah.
Okay. Okay. There we go, we got a clock. I launch. Reflect. Stop. Okay? So if I know the wave speed. If I count the clocks, I know exactly where that reflection came from, right? Let's do it again. Ready? That's a different rate. Ready? Boing! He didn't stop. Was the echo from farther away? Yeah, so it's a piece of cake. You just launch it because it's so slow, because you have the pressures. You launch a pulse, and if I had the equivalent of a confocal system, so just an optical system, I'm just looking straight ahead, and I'm just looking right around the focus, all I do is I launch the pulse, right? Then I wait, all of a sudden, boing! And then if something's a little bit deeper, boing, I get it, and that's it. That's how you make a picture. Okay, let's go to break. No. Okay, but that's the basic principles. Pulse echo is the first thing, and that gives you your axial resolution. Okay? And what kind of pulses do you actually use to do that? Well, this is actually not a state-of-the-art pulse. This is just actually a MATLAB thing I did just to stylize it for you. But typically you make a pulse which is 1 to 2 cycles. Okay. So I always used to, we did some femtosecond laser stuff when I was back in Michigan, integrating imaging system with a therapeutic system in the eye. And they used to talk about, they were so proud, because there's a big optical fast sciences center there, they were so proud that their femtosecond pulses, which are these incredibly broadband pulses. And we said, what's the bandwidth? And they said, it's femtoseconds. What's the bandwidth? It's it's like 0.00001% fractional bandwidth, right? Because that concept is everything is pretty much CW in our world as optics. Ours, when we say it's broadband, it means literally that. And typically 50 to 100% bandwidth. 1 to 2 cycles of the primary waveform. Why? Because that's our axial resolution. If we do pitch and catch, that's our point spread function. Okay? So the tighter we can make that point spread function, the better is our axial resolution. Because as pitch and catch, we go out and we come back, we can divide by 2. So if I have 2 cycles worth of waveform, that's 1 wavelength worth of resolution. Okay? So if I'm typically between 50 and 100%, then our resolution actually is typically a wavelength to half a wavelength. And that's what's done. From that, you have the Fourier transform of just the pulse itself. It's very broadband, 50% or more. Okay? So, the pulse that you put out for this pulse echo can be described in the simplest way as an envelope in a carrier. So you have the envelope A of t, be something like a Gaussian, which we typically use just like in optics. Spatially, you use a Gaussian. Here, temporally, we tend to use a Gaussian. And you have a carrier, cosine omega 0 t. And when we say we're imaging at 50 megahertz, we're imaging at 2 megahertz, we're imaging at 14 megahertz, that's the carrier frequency. Because the carrier frequency determines the wavelength, and you'll see how that comes into play in the rest of the imaging system. And then your bandwidth, okay, and that's the way these things are normally calibrated. So someone will say, I have a transducer, I have a 5 megahertz transducer with a 75% bandwidth. Okay, and that's what we're talking about, is the fractional bandwidth. And you can directly convert that into the duration of that impulse. Okay, so 50% is 2 cycles, 100% is 1 cycle, roughly. You have to take factors of pi over 2 and all that into account. Okay, so using that formalism, it's really simple to say, what's a pulse echo measurement? Right? Pulse, I have, can you see that? I was going to take the green one last night. She talked me into this. Okay.
There's a red one.
No, I don't think it works. Okay. Oh. So anyway, so this is your. So what is that? Low pulse echo? Well, just formally, that's a convolution of the wave propagating with retarded time, right? So the retarded time, it's a convolution of that with my scattering function. So we're now here, right? The scattering function in that case, where it's just a single target, would be a delta function at that distance, right? So as I go back, I will see that over this time window corresponding to the pulse, I have just the carrier frequency and then this time modulation, amplitude modulated by, and phase modulated, because you have where the exact distance is, by the strength of that scatter. Okay? So formally, very, very simple to write what that simple pulse echo experiment is doing. Okay, and I just did that, right? That's the delta function, and so what you get is just the delayed version of that original pulse you send in with carrier and envelope. Okay, so the next piece is I got my one dimension. What about the other two dimensions? Well, there we do the same thing as optics. We use lenses, but we use lenses in interesting ways because we've got time on our side. And that is here, is we now, what I'm going to do is I'm going to do a quick hand wave to tell you how we do this, and then like I said in the back notes is there's a bunch of the references in the books about how to go through this. But I'm just going to do it by analogy to what you already know, which is optics. So I'm going to say, let's look and analyze the way in which we form lenses in the CW case. Okay? So I don't have an envelope, I have a continuous wave. So just like you have in optics. So how do I then form a beam? How do I say I'm going to go in a particular direction? Well, just I'm never quite sure the exact pronunciation when I hear a Dutch person say it versus me, but anyway. The Huygens, the superposition principle, exactly like you do in optics, applies here for looking at how you're going to put together point sources into a lens. And so you have this now, but notice everything's just in terms of pressure. So it's an EIKR over R, but you have this now with the phasing of a plane wave. All right, so we're assuming a continuous wave source, superposition, and we're just going to solve the diffraction integrals, right? One thing, I'll just notice it, is everything's the same as electromagnetics here once you put it in this wave context, with the exception of our inclination factors. Our inclination factors are orthogonal to the inclination factors you have in traditional optics. So it's like the 1 minus cosine theta that you have in optics for a pinhole or open aperture. For us, the equivalent is cosine. Physically, what does that mean? What it means is your transducer is something which is baffled on the outside, and the center of it is sort of angled and pushing material this way. Okay, so it's this thing is in physical contact and pushing material this way to create pressure in the particle, a particle velocity which goes this way with an accompanying pressure. You can't move anything that way. Right? So if they're physically, the atoms, the molecules at the surface are moving this way, they can't produce any motion orthogonal to that. And that's the inclination factor. Okay? Well, I'm going to ignore it. But, just, you know, that's really the only difference you will see in these equations from what you've done in optics. So what do you do? Well, let's just do a one-dimensional one-dimensional aperture, two-dimensional case to see how this works. Well, let's assume that you have an aperture going from minus A to A, and I want to look at and say I want to see what it would take to look along this direction, angle theta, from the normal from that aperture. Okay, well, I compute the diffraction equations. All right, well, when I do that to a Fresnel approximation, again, everything's exactly analogous, is what I have is the equivalent of a point radiator out front, normalizing everything, and then I have this diffraction which has linear terms and quadratic terms, i.e. a term, and the way we always talk about it, because we're doing this electronically, is we always talk about it as a steer and a focus. Okay? So we're going to steer the beam in the direction we want and focus the beam to a particular range. But the diffraction equations are exactly the same. Okay, point radiator, diffraction integral. Okay, when you go through that, right? When you go through that, is what happens if you produce aperture functions. So what if, for example, is you were looking straight ahead and you produced an aperture function in which you varied the phase quadratically across the aperture face where the curvature of that is normalized to a particular range R, i.e. you make a lens, right? So if you take that in, the final function you'll get, because you had this term like that of the opposite phase from the propagation, will just give you a rect function. And what do you get then? Your beam pattern, that is what you would see out here, is just the Fourier transform of that. The Fourier transform of a rect is sinc, right? So what you see is a sinc function for the simple aperture if you steer along this direction, in the case I've written here is for the direction actually that's straight ahead, but you'll see that. But what's K prime? What's the Fourier transform variable? The Fourier transform variable is just exactly the angular spectrum. So again, it's identical. This is Joe Goodman, right? Straight out of that. Angular spectrum, you can do that. All the same. So you know how to do all this stuff, right? The only difference is, as we'll see, is I get to play with that steer term and that focus term because time's on my side. Okay, so now let's marry those two together. And again, I'm saying this is kind of hand wavy, and there's more details in the extra slides. But to a reasonable approximation, I can say that the actual way this imaging system will work is simply to view it as a pulse echo measurement where I am going to use diffraction and manipulate diffraction along the aperture to control the direction and focus of a propagating pulse. Okay? So I will take a pulse, which will propagate along. What I see in terms of the other two dimensions, so this is the one dimension I have here from the pulse echo, like we just did in the little experiment. And now, spatially, that will be modulated by the diffraction pattern from our aperture, okay, which is just like the lensing you would have in optics, but again, we're going to manipulate that. Okay. All right, so let's make a picture. Ready to make a picture? I think we're ready to make a picture. Okay, so phased array. How a phased array is going to work. So the picture, that's why I used that old 15-year-old image, because it is exactly the way I'm talking about here is the way it made a picture in those days. Okay? And that is, you saw it was a sector scan? Remember? Wasn't a rectangular scan, it was a sector scan. The reason is you take an aperture and you're trying to look at the heart, you have what are called acoustic windows. You only have a finite size that you can get the aperture in and not be blocked by the ribs and the lungs. So from that fixed aperture size, which is relatively small, if I just took a projection, I get a very small piece of the heart. So what you want to do is you want to expand that projection to look, and that's a classic phased array. And how do I do that? I steer the beams in the directions I want to scan out that geometry. So what I will do is I'll fire the transducer. I won't make it start the clock every time, okay? But conceptually, just think about it. Every time I fire that transducer, the clock is starting, right? So I fire. And I fire setting up the delays, the phasing on this guy, so that I will shoot a beam in a particular direction. All right? I'll get into what we do then. We're going to process this with time along range, because that's the pulse echo measurements. But after I finish that one, I'll go to the next one. I'll go to the next one. Next. Okay? And then I'll do it again. Right? I love doing this. I'll do it one more time. Oh, no. All right.
Go back.
There. Okay. Right? So you're just scanning through and through. What was it when I reset? It's a frame. Right? So I have a frame. So I go frame to frame to frame to frame. That's all you do in this, conceptually. However, we got to do stuff there. Because I said, okay, do pulse echo, I'm going to make some lenses and all that. So how do we do that? Oh, I'm sorry. Because I know you can't stop it because that stops the recording. Okay, so let's look at this from some timing. Think of the perspective of time. So what's the transmit time? The transmit says I'm going to launch a beam. All right? Now, in the old days, this is where stuff is changing into the confocal approach. But in the old days is you would go to the transducer and you fire it, and the waves would go. And once they started, once they left, you couldn't get them back. Right? Nature will give them back, but you can't get them back. Which means on transmit, you set up the phasing, you can focus, but you can only focus to one depth. Right? Does everybody get that? Once you've launched them, they're gone. And so they cohere and will come together at one depth. That's now changing how we do it, and that's a break. That's either a B or a break. Think about how you violate that and go over that. But anyway, let's just assume for now that you're a fixed focus on transmit. So what that means is, if I'm looking straight ahead, I will set up a lensing pattern, but the lensing pattern now is not a physical lens, it's a time lens. And what you say is, look, this guy takes longer to get from here to here than this guy does, so I'll fire this guy first, and I'll fire that guy later. Why? Because after they propagate, right? You can clap along to the bottom if you like, but that's your clock, right? You're going along, boom, boom. By the time you get to this time, they all cohere and you get the big signal at the focal point, right? Get that? Now, it keeps going, and so it will diverge. The focus will diverge. And before it got here, these were not in time, right? If I went backwards, those are not all time aligned. So there's a defocusing there. But there's a fairly good depth of field. So for the simplest type of imaging, a single focus still gives you adequate processing. But we'll get back perfect focusing on receive, which I'll show you in just a minute or two. Okay. So what's receive timing? So now this guy, so I went out. You're my scatterer of the day. Turned around, right? So because the clock is ticking, I know if something comes back, it's got to come from this range. So I know that. So now when this guy's going to come back, it's propagating back because it's a pulse echo, right? So it's coming back. These are now spreading. And what happens? The pulse from this guy will return earlier than that. Why? Again, the propagation path is shorter there than it is to here, right? So you have that. So what should you do if you want to make a picture at that point? Oh, you can't talk. They got to talk. What do you do? How do you know when you're in focus in this worldview? Everybody's aligned, right? Because with the diffraction integral is the sum across the aperture, right? So I'm going to take the sum across the aperture. So in order to get a big signal, I have to delay these guys. How much do I delay them? I delay them with the lens equation. And so when I delay them, that's what the received beamformer is doing. Okay? Now here's the beauty. I think this is the next slide. Well, let me just say here, there's a couple slides actually. Okay, is that I did that timing. Whoops. I did the timing for this guy. What if there was one out here? If there was one out there, what would the timing look like? It'd be less, it'd be more shallow, less steep, right? Because it goes like 1 over R, right? So if I change the delays, later, why? Well, I know where this is coming from, right? If I change the delays, I can refocus the lens for that range. Okay, you're looking at me kind of, I always look at, you're looking down, you're looking up, you guys are looking kind of like 45 degrees, which means you kind of get me, but not completely. All right? But it's just this idea is, unlike in optics, when you have this lens, the lens is focused right, and that's it, is we can change the curvature. We can change the curvature however we want. Okay? And the 3D imaging systems just do this on two-dimensional apertures, exactly the same thing. Okay? But you're changing the curvature of your lens. How do you do it? You're changing the time delays in the system. So you change the time delays in the system to align waves at a given time, which come from that point in time if there were a reflector there. Okay?
How many transducer you need to do that effectively?
Okay, so the original array systems that started 30 years ago had about 64 elements. The current array systems have about 10,000 elements.
Each one of them
Each one of them is an independent vibrator with electronic control. Okay? So that's why I said we ride this electronics curve. And it can be bigger than that. We can do a lot more stuff if we could go up another order of magnitude in elements. Okay? That's where you get the 3D. Fully sampled, two-dimensional option. Yeah?
So when you say you change the time delay, do you still only send
I mean, you could shape your pulse to focus, or your pulse delays when you send the pulses in to change your focus of your ultrasound.
Right.
And then when they come back, you can sort of, so it's kind of like you send them with only one lens, because you only make one focus when you send the pulses in, and then you pick up with a dynamic lens in the center.
Exactly right.
Change your focus.
So we call that fixed focus transmit, dynamic focus receive. And just like you said, is that I have one lens on transmit and I have an array of lenses on receive. All right? And what the modern scanners are doing, because you're doing this, you don't fire with the whole array anymore. You fire with segments of the array that are coded in a way that you can get some information back and retrospectively put back together multiple lenses on transmit. That's the new way to do it. You have all these elements. But when somebody was talking about retrospective focusing, either in the poster or something else, which I found interesting, because this is done like 10,000 elements in ultrasound now. There's like 2 or 3 elements here. And it's just because of the time limit. We have all the time in the world to do that. But exactly right. So there's this traditional way, is you have a fixed focus lens, but on receive, I have this variable focus lens. Yes? Go ahead.
So that means that you get the highest amount of signal from the point where you focus for your transmission.
Yes.
But so along your transmission line, you get a high signal at the focus, and you get a lower signal on both sides. But all your points are still kind of in focus, so you don't get a blurring. You just get a lower signal to noise ratio.
Exactly.
Okay.
And that's compensated. So you never see that in the picture. Okay? Because that's known, and that's coming. Exactly right. Everybody get that? That was very, very well described.
Could you give it this again?
Okay, so the idea is when you transmit focus is that your intensity is going to be the highest at the focus. If you're either in front or behind the focus, the acoustic field, which is illuminating the scatterers, is lower. Okay, because you're at the focus. But your receiver is exactly in focus. So in terms of spatial resolution, you're pretty darn close, whether you're in the transmit focus or away from the transmit focus, because your receiver is dominating that. All right, but your signal size goes down because you don't have as efficient a scattering event which your receiver is viewing. Okay, and so you have a distribution, and it's asymmetric about the focus. You always draw depth of field in optics as being symmetrical. We never do in acoustics. We always do it because it's 1/r, and that effect is what we're compensating for. Is we know what that change is, and so we compensate the amplitudes knowing that the fields which are illuminating at different depths go through this effect. Okay? Yeah?
You focus your ultrasound by constructive interference, but if you have constructive interference, you also have destructive interference. So there should be some point that you don't see.
No, well that's what I would say, that what you just described is a very nice way of thinking about aberrations within ultrasound. Okay? So the destructive interference that you have is why you have a beam. Right? So the energy where it's coherent is going along where the beam is. Anywhere it's outside is you have mostly destructive interference. And that's why when you launch the beam, you're really looking along one direction preferentially. But if you have aberrations, you do. Now the wave speed I said was close to constant, but it's just enough different that especially for these larger arrays that are being used now, is you'll see aberrations in there too, because you don't have that perfection. But I don't want to go into that here because I want to get onto the photoacoustic stuff. So we do it.
I think I've just realized why it is that you could get a factor of 2 improvement in this depth resolution quotient with ultrasonics then, because you can dynamically refocus on the receiver.
Oh yeah, yeah.
And you improve your signature.
Yeah. Oh, absolutely. If you don't, the original scanners from the 70s is yeah. I mean, you would see about a little piece.
But we can't do that.
You can't do that. Right. We can adapt everything. So let me get to next week, and then I'll make a little comment on that, because that will be a break point. Okay. So you transmit focus. That's why just exactly as you described. When I think of the transmit, I think I got one place I'm transmitting to, which is ideal, right? But on the receiver, every point. So the first point you go right there, I can rephase everything, right? Now here's the other thing that we do. We keep I can say it to you guys. I always never say it in the acoustics class this way, but I can keep a constant NA. I can keep a constant NA. But if I'm here, and this is the way you manage aberrations and side lobes and things like that, if I'm here, I don't have to use the whole array. Right? I use a fraction of it. So I keep a constant NA. So as I go with range, I keep increasing or opening the aperture. All right? To always make sure I have an ideal focus and a constant spatial resolution. It goes, and I just keep redoing at each line. Boom, 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 boom. Okay? And so that receive timing again. So be careful, I'm going to trick you so that I can have received elements going this way. So the pulse is now going out that way. And what I record on the array will be going this way. Okay, so I get a pulse out, it hits this, so at this time it hits this target. When am I going to see it on the array? 2 times, right? So I see that. I can rephase this guy, line it up, and I'll get my signal there. But the wave keeps propagating. So at some time later, I'll hit the second target. Right? When do those waves show up? 2 times that, so over here somewhere, right? Do they have the same curvature as this guy? No. But I can rephase that. And what I didn't show is, when you're really close, these guys may have some distortions, and so I'll just use some center elements. As I go deeper, I'll use all elements, but keep this constant NA as I go. So you have a constant spatial resolution, you have a constant in range by controlling the pulse, and you have a constant in the other 2 dimensions by controlling the aperture. Until eventually you got the full aperture open, and in the far field of all images, you'll start to see blurring, because you've run out of aperture. Okay, so receive beamformer is just the electronics to do that stuff. So this is an old picture, because I just show you, because in the old days it literally was just a digitizer, FIFO, and an adder. Nowadays, it's an AD and software. 100% software that's in there, which is what all these retrospective focusing and all this stuff, you can only really do that via software. And the GPUs, I saw a bunch of people talking about the GPUs. GPUs were introduced into real-time ultrasound beamforming about a decade ago, and they're now absolutely routine and standard. Anybody who comes into the ultrasound industry programs GPUs, because that's the way in which you do these.
Can I have a quick question? But what's about the data volume? As more detectors you have, as a larger data volume you have to deal with.
Yeah, so I always joke with some of my genomic friends, okay, when they talk about the size of genomic databases, and I say, yeah, that's about 1.5 seconds of an ultrasound scan. Okay, so it is enormous, the amounts of data. And so that's just, it keeps pushing. So that's why originally it was hardware, is primarily because of the data rates. And now it's just getting to the point that you can handle this. The compression ratio, I forget the number. Someone showed this at the conference recently. But if you look at the compression ratio from the data here versus the data that actually shows up on your phone when you're viewing this, many orders of magnitude. Okay. Right, good point. Okay. So what are the steps? Steer and focus the transmitter, manipulate the transmit pattern to get what you want, provide delays to produce high quality beams, and okay, that's fine. Then single beam imaging, again, boom, boom. You want to steer on receive, you want to steer and dynamically focus, as we've done. We want to weight this aperture to give you this constant numerical aperture, and you have to provide a control system that's doing all this in real time, okay? Now, as I said, the modern scanners, when you fire, you now don't fire from the whole array. You will fire in sort of a coded sequence of different subsegments of the array. And once you fire, at this point, now in software, everything in the system is changed dynamically. The different level of the transmit firings that were used are synthesized together to try to emulate a transmit focus, which is exactly that point. The basic receiver is dynamically changed to focus at that point, and so the way to think about it is you have a confocal image at every point. And it scans point by point by point by point by point, and then what do? Windshield wiper, right? So is real-time imaging. Here's the windshield wiper, I think. Hold on. Boom, 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 boom. Go to another one. Boom, 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 boom. Okay. Now, Now I can say what I said. Speed of sound was too fast. Speed of sound was just right. Now the speed of sound is too slow. The reason why the speed of sound is too slow, to get all this data to do these 3D volumes, I have to wait for the sound to come back to me. So we actually have limitations on frame rate versus the pixel densities that we put into our images. And so there's a lot of work there with the research community for doing different types of coding so you can parallelize that as much as possible to increase the frame rates. But our biggest concern right now is not spatial resolution, it's not aperture size, it's not that, it's frame rate. How fast we can make pictures when we're doing 4D imaging. Okay, so, yeah, sure.
So even in the modern systems, it's still kind of this windscreen wiper type of imaging, or?
Well, anytime. They have all kinds of geometry.
Yeah, but still it's a line at a time.
Not exactly. Not exactly a line at a time. So what's happening is you're having on any given firing is a subset of the transmitters which is producing. And on the receive, you're making every receive beam in parallel from that subset of transmitters. Right? Because the data's coming in, it's all this common data, right? So every beam in receive is being produced for this subset of transmitters. Then you go to another subset of transmitters, and you do the same thing. Every receive beam is put together. Then you re-phase all these little transmit things together, and that's how you get the conflocality. So in fact, and then you have motion artifacts now, so you have to play games to make sure that you're putting segments together so you can have motion artifacts in the light. So no, it's sort of the opposite. All right? But that is conceptually, though, that's why I like that, because when you get a final picture, you can think of it, there was a guy going along this rate and pulsing along like that. Okay? So, again, so we can get ourselves energized a little bit. What do you need to know? The image frame is a collection of pulse-optical recordings. Okay? Transmit beam, in the traditional systems, the transmit beam is fired once, and so you get one primary depth for your transmit focus. Okay? The total beam is the product of transmit and receive beams, which means you always have this fixed focus on transmit by dynamic focus on receive in the traditional systems. Receive is dynamic, as I just said, to get the optimal. You now know how to make an ultrasound picture. Okay? I really think it should be on your certificate. Okay? All right, so next segment, should we want to take a minute or two, or just keep going?
How are we doing for time?
I have no idea.
It's called a bio break.
A bio break. Thank you. So, yeah, just a few minutes for people to just stand up and get some fresh air.
Okay, so I got to stop because I had a
But
separate
really,
presentation. So
very
just stop and then
quickly.
start recording again.
Yeah.
Well, how do I do it?
That is in the upper left, or is it upper right? And that's a small, may even be able but it's also done in software. So you don't have a mouse pointer.
Yeah, where'd my mouse pointer go?
When you just press escape.
I did. It's
So it maybe took a time to realize.
So let's I'll take a minute. This is not computer thinking about this.
Easy to forget that you have it's like with the sound, you have to wait for it.
What's actually happened to actually imagine that speed and it's insane.
Excellent.
It's pretty amazing.
Yeah, it's not as, of course, as flexible as this because it's just a regular
Speeds.
It's an amazing.